Sorry, am I audible to all of you?
Yes, sir.
Yes, sir.
So, what you have studied till now in your digital communication course, what is the basic structure of the communication? So, what is your digital communications block diagram? Do you remember? Uh, is my this sheet PDF sheet visible to all of you?
Yes,
Yes,
sir.
sir.
Yes,
Okay.
sir.
So this is your message source, right? Which generates some random symbols or signal. Then what we do some type of source coding. Next, what we do some type of channel coding. I will explain to you. I mean, I assume that you know a bit about all of this, but I would also explain it to you. Then up to this point, we get the information in form of bits. 0, 1, 1, 0. This is intangible form of information, right? Form of information. Why am I calling it intangible? Then we are using a digital modulator. Can anybody answer this question? Why I am calling it intangible form of information? Try it. Give it a try. Anybody? Pranav? Okay, so this form of information is not physically realizable. It's just for your understanding that, okay, we are saying that this information plus a volt will be represented by 0 or minus a will be represented by 1. So it's an intangible form of information. But if you want to send this, you have to convert it to some electrical form, correct? If you want to send it through wire, you have to convert it to some electrical form. And then if you want to transfer it through wireless media, you have to also convert to it. You have to use some sinusoidal carrier, and then you have to forward or you have to transmit it over the air, correct? Now, is it clear why I'm calling it intangible?
Yes, sir.
And because it's an intangible form of information, now you need this intangible form of information to convert it to some physical form that has some existence in real life. The pulses or the modulations, this type of waveforms you need in order to transmit it through the channel, right? You cannot transfer some intangible form, or just you have just a code. You have developed some code, and you cannot say that I can transmit it. You have to transmit it in some physical form. And this filter, do you remember why do we need this filter? This is a transmit filter. See, ask questions so that I know what you know, what I should tell you. So just ask question, answer, because it's a first class. So for me, for this, for you people, so I should also know what you already know. So do you know what is this filter? Why I'm calling it a filter? Anybody? Okay. So what does filter do? This will give the shape. Suppose here till here you have bits, information in form of bits. Now you use a BPSK scheme. You say I will represent 0 by plus root p and 1 by minus root p, or vice versa. It's up to you. So you represent 0 by minus root p and 1 by plus root p. Correct? Then you will have this type of rectangular pulses, right? But when will you get this rectangular pulses? When you will pass through this, suppose this is your 0, 1, 0, 1, 1. And you represent 0 by minus root p, 1 by plus root p, 0 by minus root p, 1 by plus root p, 1 by plus root p. Correct. Then if you pass it through a rectangular filter, a filter which will give you this type of pulse, then what will happen? If the impulse response of the channel, this filter is like this, then accordingly you will get this type of pulse. Or you might have read the sync pulse, right? Sync shaping, we do this type of filtering in order to avoid ISI. Do you know that? Or excuse me, anybody? I'm just trying to understand what I want to tell you, what I should tell you.
Sir, what is the full form of ISI?
Intersymbol interference. Okay, great. So I will note it down, and when the time will come, I will tell you. So just remember that we use this type of pulse shaping in order to give the proper spectrum shaping. You know, Dr. Andrew might have told you this Manchester coding and etc. Right?
Yes, sir.
So in that, what you do, you get different type of spectrum, right? If you use A type of line coding scheme or B type of line coding scheme, the waveform which you transmit into the air through air, they have different spectrum characteristics. Correct? Up to this point, am I making sense? So similarly, I mean, in order to avoid the effect of ISI, we use this sync pulse shaping. If you not heard the Nyquist criteria of zero ISI, then maybe I will tell you by taking some extra lecture. Okay, so till now I assume that you know what is line coding, right? So
Yes,
just consider this digital modulator filter as a filter which will convert your impulses of this kind plus root p minus root p to some kind of line coding. Correct? Either Manchester or NRZ or RZ. So they will convert you to a line coding. I mean, a physical form, a rectangular pulse. And then you transmit it through air. Or not through air, through wire. Because in order to transmit it through air, you need some antenna also. Okay, so let us focus on our topic, which is like source coding and channel coding. So just I summarize whatever I have told you so that you are not confused. See, we have a message signal, message source. Then we try to encode this message source, and then we provide a channel encoder. And then we suppose you understand it as a line coding, because you know line coding. We do line coding and we transmit it through wire, for example. And then you do this reverse operation. Demodulation, detection, channel decoder, and source decoder. Source decoder, and then you get the message. And you also know that here we add some noise, right? You know that at the receiver, the noise is added.
AWGN.
AWGN channel, have you heard of this?
Yes, sir.
Yes,
Okay,
sir.
great. So if this is a AWGN channel, then what you do, you receive y is equal to x plus n. Right? This is your AWGN channel. So consider a scenario first that there is no noise in the channel. Your channel is ideal. So in that scenario, if your channel is ideal, we don't need this block. This is a channel encoder block, which try to overcome the effect of noise. Okay, so let us take an example in order to be okay. So suppose you have a message source and it can generate 3 messages. And if you want to transmit this through wire, but this is a hypothetical scenario that there is no noise. So what would be your aim? That you should represent all the masses which is coming in a very compact form. I'm just discussing source encoder first. We are not just avoid that we are using channel encoder. I would first motivate why do we need channel encoder, and then we will discuss about its functionality. First, just focus on what is source encoder. So if you want to transmit a message, or suppose you want to record a video and you want to save it into a CD, compact disc. So what would be your aim? Your aims would be that you can record this video in a minimum number of space, right? You want to compress this video as much as possible that you don't lose much information. Do not lose information. Still, you can represent your whole video in a concise or compact or compressed way. So this is your aim of using source encoding. Correct? Is this point understood? That if you have a message or video, for example, you first try to make a scheme which is such that you can represent your whole message in minimum number of bits required or minimum numbers of space required, because those bits are usually stored in this CD or in this hard disk or something, right? Is this clear?
Yes, sir.
Okay. So because this channel is ideal, so you see that you send this compact form of information and you happily say, whatever I transmit, I will receive here. But because there is no noise, the channel is ideal. Your CD is so good, the material of the CD is so good that even if you play it, there will be no scratches or nothing. So there will be no loss of information. You can understand it like that also. So the source encoder serves the purpose that you have compactly represented the information, and you have, you have not lost the information much. So this is called lossless compression also, that you try to compress your information in a very efficient manner. So that is the main functionality of your source encoder. Okay, now the question is, why are you putting this channel encoder block unnecessarily? So I say, okay, Pranav or whoever asked me the question, that if this is a message source and this is your source encoder, you have represented your message source very efficiently. For example, by using this, there are many, you can name one compressed algorithm which you use, LZ, I think, like something like that. You use in computers, we reduce zip file or something like, so it try to compress it. So source encoder. Now, but you said, sir, there is a noise, and whatever I transmit, suppose I transmit 0100, and at the receiver, some of the bits will get flipped. So how would we know that our bits are getting flipped? Because there are some errors are occurring due to this noise. So this is a practical condition. This is because in our previous example, we have considered a hypothetical channel. We said, okay, everything is perfect. We are happy. We just want our message to be represented very compactly. We want to transmit it. But there is a noise which is present in the, but when we come out of this ideal scenario and we see in practical life, there is noise which will change or flip some of the information bits. So can you do something intelligent can you come out with some algorithm or something, because you are an engineer, right? So as an engineer or as a mathematician, we should come out some scheme which says, okay, even if some of the bits will be flipped, there will be noise, there will be some type of error, we will be able to detect the errors to some extent. And possibly we will try to also correct few of the errors. So this is our motivation to using channel encoder. So now you ask, okay, sir, you have told me that you will do some magic, that channel encoder will do some magic. It will detect the errors and it will also try to correct the errors. But how would you do that? How are you going to do that? How are you going to implement that? So I would say, okay, student or Pranav or whoever asked a question, that correct. We are getting, suppose your source encoder converts your message to some bits first. And you say it's very compact form of representation. So we say, I would introduce some redundant bits here. By saying that redundant bits, for example, you say, I will add one bit in such a way that your whole message will be of even parity. What is even parity? Even parity means the number of ones are even. Up to this point is clear. You can ask if.
Sir, we only change. We only add a bit. We don't change the coding we have done.
Correct. So suppose, for example, I said the source encoder gives up to this point. This is your message, right? This is your actual information. So now you add some bits, or you add something in such a way that you can exploit this structure at the receiver. If this structure is somehow corrupted by the noise, then you will know that there is some error. So consider a scenario, there is 1 bit error. 1 bit error scenario. What would happen? Just change one of the bit of this message. Just say anyone. I will write. Change any of the bit. The condition is there should be only 1 bit error. This is your message, which you have converted with source encoder, for example. And now you say there is only 1 bit in error. This can also be an error, because now this channel goes, this is the message, this is the message part. Now channel encoder adds a 1 in order to make the total number of ones in a message is in a frame or in a structure is even. So because it is 1, so we add 1 more 1 so that it is 2 now. The number of ones are 2. So it is even, right? Now this bit sequence passes through the channel, and I say there is only 1 bit error event. The event is, if somebody asks you, this is the event which is occurring in the channel, that 1 bit is in error. So just change any of the bit. Anybody? This is the transmit sequence. This is your channel, and the channel flips 1 of the bits. Just change anything. Just speak up.
11000001.
Great. So now, how many? Just you count the number of ones. How many ones is there?
3.
3. But you told that I have used a structure while transmitting that will have even number of ones. But at the receiver, you counted number of ones and you told that it is odd. So you can say that an event has occurred which is 1 bit is in error. At least 1 bit is in error. Can you say that? by counting number of ones at the receiver.
Yes, sir.
So how intelligently you have put some redundancy, but in an intelligent manner, which you exploited at the receiver, and you said, sir, I have detected this event. You are a receiver agent, detects that there is one bit in error, at least one bit is in error, because it might be the scenario that, okay, if two one changes, then you can say that, okay, sir, this is also even parity. But I said the channel is such that it only changes one bit. So this is an example. So I am just trying to motivate that how this channel encoder can help you to exploit, to help you to find out if there is an error. Okay, take one more example. Just I'm trying to motivate, okay? Just try to understand that you transmit 0100 sequence, and you say that this is your message. This is your source encoder says that this is your best compact form of information. Now the channel encode, you say at the channel, this input goes to channel encoder. And you say that I will repeat each bit 3 times. Something like that. Correct? And so if you see that if any bit is in error, suppose for example, this goes to the channel and the channel changes something like that. 011 001. At the receiver, you count, you just check it, okay? So at the receiver, by seeing this, how would you, what would you try to infer? Number that, because the number of zeros, so this is a separate example, okay? This is called repetition. We just, for example, if there is a noise in the channel, then in mobile and two people are talking over mobile, what they do, they say same sentence 2 times, right? Hello, hello, hello. So even if one hello is corrupted by noise, at least you have 2 hellos, right? Something like that. Just I mean, because I'm here motivating, so just try, just you repeat each bit 3 times. And at the receiver, you just first count 3 bits. So you see here that number of zeros are 2 here and number of 1 is 1. So you decide in favor of 0. Here you decide in favor of 1. Here you decide in favor of 0. Here you decide in favor of 1. Here you decide in favor of 0. And what was your original message? 01000. 01000.
But sir, so this example feels like it's only designed for hello, hello, hello. Like for a normal sentence, you will not repeat it twice or thrice.
No, we do it. In repetition coding, what we do, we repeat each bits. If somebody say that we are using a channel encoder which use repetition coding. So in repetition coding, what we do, whatever information we receive from source encoder, if we say that, okay, we are using 3 time repetition coding, then it will do exactly what I have written here. Just try to just go and read repetition coding. What is repetition coding? You will see that. So here, even if, see that the bits are in, for example, here also you have only 1 bit in error. So you can get the message, the received and the transmitted will be same. Now ask question. So in a, you can think it that you put an algebraic structure in a very intelligent manner, and if it get disturbed, you can check it at the receiver that something bad has happened and there is some error has occurred. So this is called detection. And if you can also correct those errors, then you say that, okay, there is some type of You can also correct, for example, in repetition coding, as in this example we have seen, then we can say, okay, our channel encoder also has a capability of correcting the errors. And in parity, example of the parity bit, we have only ability of detecting the error. So,
sir,
up to this point, yeah, ask.
So then you use the same algorithm in source decoder and source encoder, right?
See, what I said, source encoder, what we do, we say we have a message source, which for example generate 3 messages only with some probability. 2 by 6. Okay, take it with equal probability, for example. Then how should I represent this message? So A, B, C. Suppose this message sequence generate only 3 A, B, C. So each time you press a button, either A or B or C will be generated. So A, B, C, 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 B, B, A, something will be generated, right? So your source encoder, what does your source encoder does? It will try to assign number of bits to A and B and C in such a way that the average length of this whatever message it can provide will be minimum. So you can represent your message in a compact form. For example, in English language, this is a very standard example you also get in textbooks, that in English language, some of the, for example, vowels comes frequently. When you speak English, then the vowels come more frequently, and X and Z, these letters come less frequently. So what happens? We provide more number of bits to X if length of the bit. Okay, first ask question. What was your question? If maybe I am not.
Yes, sir. So I was saying, when you transmit it on the channel encoder and decoder, you have the same algorithms to encode and decode.
In channel encoder, we have some whatever structure we develop at the encoder, we do some reverse of that in the decoder.
Yes, sir.
This is for the channel encoder. Okay, that you have understood.
Yes,
now
for real. Yes, sir. So for in a real life scenario. So sir, all the encoders and decoders in a country are same, because you can use only one kind of algorithm at a time.
Yeah. It depends on the application, because suppose there are many type of channel encoder possible.
Yes, for a specific application, then all the encoder and decoder will be same.
For example, we use in our mobile phone convolution channel encoder. That I will teach you in the subsequent classes. That we still use channel encoder. That is called convolutional encoder and decoder. So, and there is one more LDPC decoder. So there are many encoders and channel encoders possible, but they will improve the performance by adding some type of structure. As I told you, that each channel encoder or decoder will give you some structure, and if the channel corrupt this structure, you will be able to somehow recognize, and you will be able to also correct some of the errors by using this structure. So there are so if there is A, suppose there are 3 channel encoders, A1, B1, C1, for example, LDPC, convolutional. So the complexity of each encoder and decoder will be different, and their performance will be different. So depending on the application, we use some decoder scheme or some encoder or decoder. So this is for the channel encoder. And ask a question for the source. You asked something.
No, sir, it's fine. I'm clear.
Now everything, I mean, not everything, but your question is answered, I think.
Yes, sir.
So, I mean, you can also develop some algorithm, of course, if you can, because in compression, I think people still develop some things, new things. If I talk about if I talk in the context of source encoder and decoder, so I think you people do it. So just try to search new source encoder and decoder and the channel. So I motivated that if the channel was perfect, so we need only this block, source encoder block, This is your message. But because you want some of the errors to be corrected and detected and as well as corrected, so you use this channel encoder. So up to this point, I think I have made why we have developed a course, a unit that is called channel error correcting course, right? Error correcting course, correct. Error correcting course. So what channel encoder does, it provide you the codes which can correct the error. That is why it is called error correcting course. So I think motivation is clear, right? For both source encoder and channel encoder.
Yes, sir.
Okay, everybody? Only Pranav speaks. Nobody else is speaking. So I assume that, okay, everything is clear. Okay, so now the motivation is clear. Okay, so just take an example first. A, B, and C. If your message generates only A, B, and C, with A has a probability, with probability 1/3, 1/6, and 1/2. So this is clear. When I say a source generates only 3 symbols with this probability, is this clear, or I should explain it in a practical way? So think it like that every time you switch on this, it will provide you either A or B or C. So if you just turn it on 10 to the power 4 times, for example, so it will give you some strings of A, B, B, C, B, C, B, C, C, A, B, 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 like this. So out of 10 to the power 4 times, 10 to the power 4 into 1 by times, it will generate A. 10 to the power 4 into 1/6 times, it will generate B. And 10 to the power 4 times into 1/2 times, it will generate C. So this is when I say a message source generates 3 symbols with probability this. So this is the physical meaning of when I say this. Is clear? Not this? Not clear?
Yes. Yes, sir.
Okay. Okay, Mohit. Great. So now the question is, how should, because your message source only generates 3 symbols, so you have to provide some number of bits, for example, to A, some number of bits to B, and some number of bits to C. So if A Pranav says, I will use some coding scheme. Utkarsh says, I hope there is one person at least in the class whose name is Utkarsh. Yeah, it is there, Utkarsh Singh. Because I just saw it actually. So Pranav says, I will give A0, B01, and say C001. Utkarsh says, no, Pranav, I will do something else. I will give 00 to A, 10 to B, and 01 to C. Now, what do you think? Which will be good? Or there is one more scheme, suppose, for example. I do not take, I mean, if there is some name I have to take. Aryan, great. Aryan says, I will use some this. So see, if just we are now zooming in on this part, source encoder, okay? This is your message source, and this is your source encoder. What was the main purpose of using source encoder? To represent the information in the compact form. So this is a layman. We discussed everything till now as a layman, but now we will go to some extent, at least in maths, right? Okay. So so what do you think? This scheme is good, or this scheme is good, or this scheme is good? So firstly, we would check that there should not be any ambiguity, right? By ambiguity, I mean, if I receive this type of sequence and I try to use this mapping, this table, okay, you use the table of Pranav. It says when 0 comes, we say A. When 0, 1 comes, we say B. So when 0 comes, we say A. And when B comes, we say 0, 1, B. 0, 1 comes, we say B. So there is an ambiguity that we should wait for the next, or we should take the decision up to this part, this extent only. There is an ambiguity, like, right? You can also say A, and then if there is 1, 0, there is only 0, 0, 1. So similarly, there is this ambiguity that, okay, you can say 0, 1 is B. You can then say 0, 0, 1 means C. So, I mean, using the same table, person 1 will make out that, okay, you transmit your message source, message symbols were something else like BC, or your person 2 will say, no, okay, it was A, then it was 1, 0. So I mean, these codes are not good codes because they are generating ambiguity, right? So that is why we call that your code should be instantaneous. Because at the instant we see 0, we should be able to make out it is A. We should not wait for the extent that, okay, we will first wait for the next extent, then we'll take, okay, B, it is B. Okay, so is this little, I mean, clear a bit, or what is the meaning of ambiguity? Chinmay?
Yes.
Devansh? No. Okay. Himanshu? I mean, no, it's not clear.
No, sir, it's clear.
No, sir, it's okay. It's clear. Just try to read a book also, so that it will give you more examples and better understanding of whatever. But I'm just giving you an idea that the codes will be such that they should not give you the ambiguity, right? They should be very clear in picture that, okay, if up to this point we should wait, and after that we should take the decision that A was transmit, A was the message source, or the B or the C. Okay. So since you are a computer science guy, I will tell you a best way to design a code. I mean, you can do that. So if I say that 0 was A and then I say 0, 0 was V, do you think this is a good code?
No, sir.
Huh? Not right? No.
No,
The answer is no.
No.
Because if your 0, 0 comes, one can say it is AA, or the other person can say it is B. Correct? By observing the sequence 0, 0, one can say the A was transmitted twice, and the person 2 can say B was. So this is not a very good way of coding. So if you have put at any branch, you have put at any node A, you should discard the other branches, right? So you have to discard something like that. Now you have to put B here and C here. For example, if someone does this type of coding scheme, what do you think it is good? 0, 1. We'll put A here. We'll discard the other 0, 1. This is a good scheme, right? Just take any example of sequence like 1, 0, 0, 0, 1. So if 1 comes, because you have to take decision up to this point, right? These are 3 decision making points. So 1, 1 There is no 1, 1, 0 is there, right? B. Now you take 0, A, there is no ambiguity, A, and you say 1, then it is nothing. And then you have to see other in order to take the decision. So this is called prefix-free codes. It means there is no other code which is prefix of the other code. So if we put one symbol or one message symbol at one node, we have to discard its child branches, right? So that A is not a prefix of any other code. So this is called prefix-free code. So always the source encoder try to generate prefix-free codes. Okay. Now, up to this point, am I making sense?
Yes, sir.
Okay. So I'm just giving you a brief idea that because the source encoder is actually not a part of your syllabus, but I'm just giving you, that is why I'm giving you a brief idea of source encoder, what this source encoder does. Okay. That it will try to provide or assign bits to each messages in such a way that it is in compact form. And once, but the compactness is the last goal, last mile goal, right? But it should be unambiguous also, right? But if it is not very clearly at the output of your source encoder, you can detect what you have transmitted, then there is no point of compactness. So it should be non-ambiguous, right? So one way of generating non-ambiguous codes using prefix-free code. Okay, so now the question is, can you give an algorithm which says, for example, A, B, C. You can generate many prefix-free codes. One was this. This is also a prefix-free code, right? I'm just trying to create examples and trying to motivate, and so that you go and read this thing. It's a very interesting field. Okay. Okay, just see that this is your message, which I told you that it is the 1/6, 1/6, 1/2. So these are two examples. So these two are both are the prefix-free codes, right? Pranav, Jayesh, I mean, can you make out that it is a prefix-free code? Sangini, Tanvi, anybody? Why am I calling it a prefix-free code? Because once we put a code word or once we put a symbol at this point, suppose you assign 0 to A, 1, 0 to B, 1, 1 to C. So once we put something at the node, we discard its child branches, so that any code word is not a prefix of the other code. Like if you go like this, there should not be any other code, any other symbol. Sorry, code is confusing. Any other symbol. Similarly, this is also one way that you say, okay, 1, you can assign 1, 0 to it, 1, 1, 0 to it, 1, 1, 1 to C. So these are two possible way of generating prefix-free code, right? Shivam, not clear? Banu?
Yes, sir.
Is it clear up to this point?
Sir, in example 2, you have not written anything after 0. First branch.
So we are not assigning any. I'm just saying that this is also a valid prefix-free code, because once we put.
Sir, if a code comes this way 0010.
What 00?
10.
Okay.
So how will we write the code for this?
So you are saying if the sequence come like this?
Yes, sir.
But why would it come like this? Because you can generate only ABC. So it will always come like this, A. Because whatever you assign, you will generate according to that, no?
Okay, sir.
Now is it clear?
Yes, sir.
Okay, now I understand why you get confused. Because in those examples, I just arbitrarily.
Yes, sir. Yes,
oh,
sir. Yes.
sorry, I excuse me for that. Because you only, it's not like arbitrary, because whatever you transmit, then only you will generate it, right? So this will never happen, right? Now I understand. Yes. Okay. That is why you were silent. Okay, just pardon me for that, because in earlier it was just a motivation, because I was just trying to motivate. Just okay. Sorry for that.
Yes.
So this will never happen. Sorry. Now is it clear that these two are valid prefix-free codes? Oh, yes. Prefix-free way of generating, don't use the word. I mean, the source encoder can either do this or do this. Now is it clear?
Yes, sir. Thank you.
Both, yeah, okay. And both are prefix-free codes. But as you see, what is the average length of this code and average length of this scheme? Tell me, who asked the question? I appreciate that. Who asked this question? Bhanu, you asked, right?
Yes, sir.
Okay, great. So Bhanu, tell me, what is the average length of this scheme and average length of this scheme? So you can ask, sir, what is the definition of average length if you want?
Yes, sir. The minimum is 1 or maximum is that we have to do that?
No. The average means whenever somebody asks you what is the average of something, you just think it like that. We take a long sequence, right? And we average it out. So if your source is generating A, B, B, C, D, C, A, B, B, something like that, and you assign, what did you say that I will assign A0, B10. So you assign some 0, 1, or just an example, B is 10, C is 11, B is 10, C is 11. So you will do similar thing like this, okay? So the length of the code, length is 1 for this, 2 for this, 2 for this. So if we generate a large sequence, for example, 10 to the power 4, I told you out of 10 to the power 4, 10 to the power 4 into 1 by 3 times A will be generated. Out of 10 to the power 4 times 1 by 6 times B will be generated out of 10 to the power 4 into, because this is the probability which I told you, right? When I told you that this is a massive source which generate A, B, C with this probability distribution or this probability. So this is, I think I explained this, what is the meaning of this thing, right?
Yes, sir.
Okay, so when I asked you average length, so you said I will give 1 bit to A, 2 bit to B, and 2 bit to C. So what is, I mean, take the average. Out of 10 to the power 4 times, 10 to the power 4 into 1 by 3 times, you will give 1 length, I mean 1 bit to A, I mean, because this is the probability of A, right? If not probability, because probability is this number of times the A occurs. So every time A occurs, you will give 1 to A, 1 bit length, because it is 0, right? Don't confuse it. This is length. So out of 10 to the power 4 into 1 by 6 times B occurs, and you assign 10 to B, it means 2 bit. Out of 10 to the power 4 into 1 by 2 times C occurs, and you assign 1 to C, so it is 2. So what is the average length? Oh my God, why the pen is not working? Out of, because you have to define total number, right? So out of 10 to the power 4 times, you perform an experiment or you generate some symbols sequence ABC ABC, out of 10 to the power 4 times 10 to the power 4 into 1 by 3 times A is generated, and each time A is generated you assign 0 to A, so length is 1. So what is the average length now?
So 4 by 3.
This is the average length. 1 is to 1 by 3 plus 2 is to 1 by 6 plus 2 is to 1 by 3. This is the average length of code 1, right?
Yes, sir.
Yes, sir.
See, I could have done it very in a straight manner, that average is defined as expected value of the length provided to each x, where x can take 3 values. It's very simple for me to write like this. So LA into what is the probability of A, LB into what is the probability of B, and LC into what is the probability of C. This is the average length. If I want mathematically, see, defining mathematically something is very simple. But you have to understand that what is the meaning of average length. Out of many times, if A occurs this number of times, you will assign 0 to A. So what is the length of, will be the length of your code? 1 bit out of 10. So this is the, you can write your average length. This is the definition. Okay. Now say what is the, if somebody use scheme 2, what is the average length? Tell me, Bhanu.
Sir, just a second, sir.
Yeah. Sure. There is 2 ways to understand the average length. Either this practically, or you can also see the definition. So what is the length? LA is 2, LB is 3, LC is 3, right? Because you are assigning 3 bits to B, 2 bits to A, 3 bits to C. So LA is 2, LB is 3, LC is 3. Right?
Sir, 8 by 3.
Oh, you have calculated the exact. No, I did not want to exact. Okay, great. If you have done that, so okay, 1 by 3 times you assign 2, 1 by 6 times you assign 3, and 1 by whatever, I forget, 1 by 2 times
2.
Times 3. So this you will see is more, right? So number of bits required in average sense for scheme 2 is more than scheme 1. So you will say scheme 1 is better because it is giving you a more compact form of representation of this message source, ABC, which is representing, which is giving this. If this is your message source, mathematically your message source, you can say like that. This is your message source. And you say that on average, if scheme 1 is better than scheme 2. Scheme 1 is more efficient, right? Because it is giving you less number of bits on average. Average length of the code is less. Right? Just tell me, do you have any other class after that?
Yes, sir, we have a class.
Okay, so we'll just finish it in 5 minutes. 5 minutes is okay?
Yes, sir.
Yes,
okay,
sir.
so what we have done till now, can anybody summarize the lecture? We have motivated ourselves. Why should we use source encoder and channel encoder? If you have a message source, right? I think just try to, this we have done. Then we have seen the channel encoder. There's some repetition coding and these things. Just try to make the examples. I pardon for that making a wrong example, but try to make an example, then you will understand better. And also we have seen what is the source encoder does. It compress the information and it will, so the channel encoder does the exact opposite job. It reduces the redundancy or removes the redundancy by compressing or by compactly representing your message source, and this will add up the redundancy or add up some bits, but in a very intelligent manner, that it will give you some structure, and if this structure is disturbed in the channel, you can somehow identify that the error event has occurred, and you can also rectify sometimes. And then we have seen that the source encoder, the codes should be prefix free. Try to be prefix free. Or I mean, if you see books, they will also tell you it should be instantaneous and uniquely decodable. Uniquely decodable means there should not be any ambiguity, as we discussed. And instantaneous means you, as soon as you get some, you should not wait for that. I mean, you should know the instant over which you have to take the decision. It's not like that 0, and then you wait for this, that 01 is also coming. So just this is called instantaneous. So the code should be instantaneous. It should be uniquely decodable, and the prefix-free codes actually fulfill both of these criteria. They are uniquely decodable, and because we have seen this in the lecture. Now you can ask question if you want. We have 3 minutes. Okay, so I think we'll discuss in the next class that I mean, as I told you that there can be many prefix-free codes. So I mean, what should be the minimum average length required for a good prefix-free code? We will discuss it in the next class. Okay.